Hello, hello, and welcome back to CS 500 Design and Analysis of Algorithms. We are currently in Chapter 2, recalling some special data structures, 3 data structures from CS 300, namely AVL trees, and we saw AVL trees are very good at many operations, specifically at insert and delete and search, because they have a small depth. They are very shallow trees, but they have a deficiency, namely merging to AVL trees cannot be done efficiently. It requires time O of n. Well, the naive algorithm will take n log n, but it can be accelerated to O of n, but not to further. What we want is merging in time log n. So the same asymptotic and optimal running time as for searching, for insert, and for delete. We also want logarithmic time for merging. And AVL trees cannot support that. That's why we instead discuss new data structures, and we've started talking about binomial trees and binomial heaps, also known as binomial forests, which are collections of binomial trees. So let me remind you of binomial trees by sharing the slide. So binomial trees, what were binomial trees? We gave 2 equivalent definitions. One definition is that a binomial tree is defined recursively, kind of like induction. Binomial tree of order k is 2 binomial trees of order k minus 1 glued together. That's the first perspective. 2 binomial trees of order k minus 1 glued together to make a binomial tree of order k. That's the induction step. And binomial tree of order 0, that's just a single node. That's one perspective. And here you see some examples of these binomial trees according to this inductive definition. But there's another way of looking at binomial trees of order k, namely a binomial tree of order k is a single root to which are attached binomial trees of order k minus 1, k minus 2, and so on, order 1 and order 0. So this is a kind of like, you know, the difference between strict induction and which is sometimes called mathematical inductions. So in discrete mathematics, you saw induction means that we take the induction hypothesis for k minus 1, whereas mathematical induction means we take the induction hypothesis for k minus 1 and for k minus 2 and for all smaller k. And we know that logically both are equivalent. And here it turns out that also in terms of data structures, these trees are equivalent. And we formulated a lemma, namely that a binomial tree of order k has 2 to the k nodes, exactly 2 to the k. So we cannot have any number of nodes that is not the power of 2. That's a severe restriction of binomial trees, which leads us to consider binomial heaps. And binomial tree of order k has height k and maximum degree k. Precisely, k over d nodes are at depth d. So that's what we talked last time. And what we impose also is that the binomial trees we consider are heap ordered with respect to the key values in the nodes, which means that the smallest key must be in the root and all children key must be at least as large. So that's different from search trees where all nodes to the left must be smaller and all nodes to the right must be larger. But here it's not left and right, but here it's bottom and top on bottom condition. And the goal is, of course, to maintain this property through the insert and delete operations. And one operation that is easy to implement is the merge operation, because if we want to merge two binomial trees of order k to obtain a binomial tree of order k plus 1, we simply need to find out which of the two binomial trees of order k has the smaller key value in its root, because that will become the dominant part of the new larger binomial tree, and the other one will become the yes, the child of the new binomial tree. So yes, and you remember that picture of how to look at that. And now, surprise, surprise, we're going to conduct a quiz. So I would like you to actually prove by induction the following 4 properties. First, as claimed in the lemma, that binomial tree of order k has 2 to the k nodes. According to this inductive definition, I'd like you to prove by induction binomial tree of order k has height k, has maximum degree k, and finally I'd like to prove that this definition is equivalent to this, namely that binomial tree of order k is a root connected to children of order 0, 1, and so on up to bk minus 1. So please conduct the quiz, write the answers to the problems first in your favorite text editor, and then please post them in the chat. And you have, let's say, you have 15 minutes to do that. So please post in the chat your name and ID, followed by the solution to the answers to these problems. Please prepare that in a text editor and then submit it maybe item by item, so that you have, if you run out of time, then you still have at least some of these problems solved. So yes, now I'm going to stop recording and stop the video, and we'll resume in 15 minutes. Good luck. And here we are back online, resuming regular lecture content. Thank you very much for participating in this quiz. So we just talked about binomial trees, and now we can proceed to talk about binomial heaps, which are collections of binomial trees. Collections in such a way that now we can finally store arbitrary number of nodes, not just powers of 2, by collecting binomial trees of appropriate arity. And this is a similar kind of like a binary representation of integers. You know, every integer has a unique binary representation, a unique number of least significant bit of weight 1, number of next significant bit of weight 2, of weight 4, of weight 8, of weight 16, and so on. So all the weights in a binary expansion of an integer are exactly the number of nodes in some binomial tree. And we can represent every integer in such a binary representation where every digit is either 0 or 1. And when a binomial heap, there similarly is a collection of binomial trees. Each binomial tree of every order either occurs once or not at all. So we don't have repeated occurrence of binomial trees of the same order. Similarly, that in binary representation, we don't have repeated occurrence of, let's say, the digit with weight 8. The digit with weight 8 is either present once or not at all. And similarly, in the binomial heap, binomial tree of order 3, corresponding to 8 nodes, is either present or not, but not repeatedly. So here's the more formal definition. A binomial heap is a list of binomial trees, ascending list in strictly increasing order that makes sure that every binomial tree of given order occurs at most once. And that's the condition here. For each k, at most one binomial tree of order k is present. And here you see an example. And recall the binary expansion of the number 13. The binary expansion of the number 13 has weight 8 occurring once, weight 4 occurring once, and weight 1 occurring once. 8 plus 4 plus 1, that's 13. That's a unique binary expansion of 13. And similarly, when storing 13 nodes in a binomial heap, that means that there's precisely one binomial tree of order 3, precisely one binomial tree of order 2, and precisely one binomial tree of order 0. And you here see such example binary trees, and you also see that they are indeed heap ordered, right? The least element is in the node, and all elements below the node are larger. And recursively here, the least element of this binomial subtree of order 2, this least element is in the root, and all elements in its children are larger. And same here. So these are all heap ordered binomial trees, and each order occurs at most once. So this is a binomial heap of 13 elements corresponding to the binary expansion of 13. And now let's recall our properties of binomial trees and then derive quantitative properties of binomial heap. Namely, we observe that in a binomial tree, every vertex has degree at most log n, the number of nodes, and every binomial tree has depth at most log n, the number of nodes. This is simply by solving this equation for k taking the logarithm. That means the height and the degree are logarithmic in n, the number of nodes in the tree. And and furthermore, we observe that according to the binary expansion of n has at most log n non-zero digits, and therefore binomial heap of n elements has at most log n different binomial trees. So putting things together, we observe that the length of this list here, which is the number of binomial trees in the binomial heap, is at most log n, and the degree of every vertex is at most log n. That's true for all binomial trees in the heap, and that's trivially true for the roots, because the roots now just, this is a linked list, so the root degree increases by at most 2, which is a constant and ignored in the logarithm. And the depth, as we observed, is still at most logarithm. So everything basically, quantitative property of binomial heaps is logarithmic in the number of nodes, which is, as you recall, good when we now discuss algorithms that operate on binomial trees and binomial heaps, because we want algorithms that operate in logarithmic time. Every operation should now be feasible in logarithmic time, including the new merge operation. So let's just wrap up the definition of binomial heap, some minor details about the new pointers that we add, right? So here we have pointers in the binomial trees from root to its children, from children to its grandchildren. We don't actually need pointers up. That's one detail. And the other detail in the linked list, so pointers to children, not the other way around. Well, yes, and the other way around. So bidirectional pointers. And same for the linked list, pointers to the left sibling and to the next binomial tree. So here we see these pointers corresponding to the ascending order, increasing in order, and here we have also pointers to the siblings, but this doesn't increase the degree by more than a constant. So still everything is logarithmic degree, logarithmic depth, logarithmic length. Okay, and now we can start talking about operations on binomial heaps. And yeah, here's our example from previously, right? So this is the same example. So a binomial tree is an ordered tree defined recursively. We have a heap order. The value in the node must be smaller or equal to the value in all the children. So that's different from a search tree, where the values in the left subtree must be less or equal to the value in the root, less or equal to the value in the right subtree. So here it's not left, right. Here it's top, bottom. Top is the smallest element in a binomial tree, single tree. And a binomial heap is a list of binomial trees, distinct binomial trees of distinct orders. So every binomial tree order can occur at most once. And these binomial trees are in that list in strictly increasing order. Now, which operations are supported by binomial heaps? There are 3 main operations, and the other operations are simply kind of easy applications of these 3 operations. And among the 3 operations, the most important one, the workhorse that does all the work for all the other operations, is the merge operation. So here really the focus is on the merge operation. So let me remind you of the operations supported by a binomial heap. First, there's a grade operation. Then there's an ExtractMin operation. There's the merge operation, the most important one, the insert operation, DecreaseKey operation, delete operation. And all these operations operate on binomial heaps and on nodes on binomial heaps. So for example, if we want to delete a node from the binomial heap, then we need to have a handle on that node within the binomial heap. Technically, imagine that to be a pointer. And how can we obtain such a pointer as a user who wants to use a binomial heap? Well, when we insert an operation, here fourth operation, then the binomial heap data type will return a pointer, a handle to that node, which will remain valid throughout the entire operation. So although the binomial heap may change, so it's kind of a persistent data structure, although it may change, the handle to the element we have inserted will remain the same. The element may be moved around from one tree to another in the binomial heap. Lots of things can happen, but the handle, that's kind of the unique identifier. And later, if we want to delete and remove that element from the binomial heap, then that's where the handle is used again for the delete operation. So imagine in an implementation, the insert operation has as argument a binomial heap and returns as value a handle of the inserted element. And the delete operation has 2 arguments, a binomial heap and the handle that was returned earlier. And the delete operation returns the modified binomial heap, or just changes the binomial heap implicitly. Right, so binomial heaps are a great example for object-oriented programming, for information hiding, so that on the one hand, and we're going to discuss how to implement these operations, and on the other hand, later, when we or somebody else uses a binomial heap, we can forget about the implementation details and just use these operations higher level operations, adding another level of abstraction to process the data in this binomial heap. So that's kind of a, the general perspective. And so, yes, as I keep emphasizing, right, that's here, the merge operation is the workhorse. And we will discuss and recall the merge operation 2 slides later in detail, but we will already make use of the merge operation. So for example, the insert operation, item 4, is an easy combination of create a one-element binomial heap with the element to be inserted that makes a one-element binomial heap, and then merging this one-element binomial heap with the existing binomial heap. So that's kind of the general reduction technique that we know from logic, from mathematics, and again from computer science. Similarly, the ExtractMin operation, together with the DecreaseKey operation, allows for easily implementing the delete operation. Namely, when the user wants us to delete a node, an element, then we first decrease its key value to be something very small, something smaller than all other nodes. There are finitely many nodes, so we can always find a, let's say, integer which is smaller than all the key values in the existing nodes in the binomial heap. We decrease the key value of the node we want to delete to become smaller. After having thus decreased the key value, the node we want to delete is now the minimum node. So now we can invoke the ExtractMin operation and thus recover that node and remove that node. That's the semantics of ExtractMin. Recover that node and remove that node. So also delete operation is a simple combination. So create one element binomial heap is also kind of trivial, right? So we create a one element binomial tree and then turn that into a one element binomial heap. So what really is interesting and what we'll discuss on the next slide are the two operations, ExtractMin and DecreaseKey. And one slide after that, we're going to spend quite some time to discuss and recall the merge operation. So let's do that. ExtractMin and DecreaseKey. And may have noticed that pedagogically speaking, we're really kind of climbing up from very simple to more and more difficult. That's on purpose. Right, so let's first discuss the ExtractMin operation. ExtractMin, the semantics has two kind of combinations. First, find the node with smallest key value, and then delete that node from the binomial heap. How can we find the smallest node within a binomial tree? The smallest node is its root by the very definition. So that can be found in constant time. Just look at the root. But deleting the root will create orphans. So we will need to discuss how to what to do with the orphans. And before finding the binomial tree which contains the smallest node, we first have to walk through the list to find which binomial tree has the smallest root. But fortunately, there are at most logarithmically many binomial trees within the binomial heap. So we're going to walk through the entire list and keep track of the smallest root we've encountered so far. And after we've arrived at the end of the list in logarithmically many steps, we've found the smallest root, and thus the root of the binomial tree within the binomial heap that we're going to remove. So let's say, for the sake of example, that this is the smallest root, and now we're going to remove that from that binomial tree. First, we're going to unlink the binomial tree from the binomial heap, right? That's easy in constant time by redirecting the pointers. And now taking care of the binomial tree, unlinking its root. That's the ExtractMin operation. But now we have all these orphans, right? But the good thing is these orphans are already, remember the mathematical inductive definitions of a binomial heap is, a binomial tree is that it is a one root with attached binomial trees of all smaller orders, So what we now do is to take care of these orphans, we turn them into another linked list. Well, we do that actually while we unlink the node, the root. And now we've obtained another binomial heap, right? Because this list of binomial trees of strictly increasing order is exactly satisfying the definition of a binomial heap. So now we have two binomial heaps, the one where we've just removed one binomial tree and the one we've just created from the orphans. And what remains to do is to merge them back again into one single binomial heap. And that's where our workhorse, the merge operation, comes into play. But as promised, the merge operation is explained in the next slide. On this slide, we want to discuss also the other operations, so that concludes our discussing of ExtractMin. And now let's discuss the DecreaseKey operation. What is the difficulty of the DecreaseKey operation? DecreaseKey operation may result in a violation of the heap order, right? So here's the example. Suppose the user wants us to decrease the key value of this leaf. Current value is 53. It's the largest value in the entire binomial tree here. And the user wants us to decrease that down to 17. And now the heap order is violated, right? So now 17 is not greater than, so now 33 is not the smallest element anymore. So we have to now kind of repair that. And we can do that by swapping these two nodes. Swapping nodes doesn't move memory, just replaces or changes pointers, right? So this node, which used to be the parent of 33, is then going to be the parent of 17. And 17 used to be the child of 33, is going to be the parent of 33. So we kind of change, adjust pointers for this new order. And now we have recovered the heap order with these two nodes, but then we have created a violation with the heap order with these two nodes. So we keep on changing these two nodes, and it's kind of like bubbling up, right? So 17, so originally the largest, heaviest element are at the bottom, or leaves. The lighter elements are up. Now we have created a very light element, and we need to kind of bubble up that light element like bubbles in water, right? Bubbles of air are lighter than the surrounding water, so it moves up. And that's what we do here, right? And we keep doing that until either we arrive at the root or until the heap order is restored, which happens here before we arrive at the root. Here the heap order is restored, and we can stop bubbling up earlier. In either case, the number of operations of bubbling up operations is at most the height, and the height, as we observed, is at most logarithmic, right? The tree depth. So that the bubbling up costs at most logarithmic time, and that concludes our discussion of the DecreaseKey operation. So on this slide, we just discussed ExtractMin. I still owe you the discussion of the merge operation, and we've just concluded discussing of the DecreaseKey operation. So that's all for these two operations, and now the real workhorse, as promised, the merge operation. And this is a very nice operation. It's kind of a generalization of binary addition of integers. And the first observation is, like every integer has a unique binary expansion, a unique way of expressing it as a sum of powers of 2. Similarly, every binomial tree has a size, a power of 2, and every binomial heap has a unique number of binomial trees of different orders, of different sizes, since every size is a power of 2, and that corresponds to the binary expansion. So, for example, the binary expansion of 23 is, depending on whether least significant bit comes first or most significant, I'm going to say the binary expansion of 23 with least significant bit first, which is maybe unusual in practice. So binary expansion of 23 with least significant bit first is 1, 1, 1, 0, 1. And similarly, a binomial heap with 23 elements consists of one binomial tree of order 0, one binomial tree of order 1, one binomial tree of order 2, no binomial trees of order 3, one binomial tree of order 4, corresponding to binary expansion 1, 1, 1, 0, 1, in increasing order of weight of the binary digits. So the opposite order that one often or usually writes in Western notation, writes binary digits. So here's the corresponding simple sum of binary powers of 2 corresponding to that. And now to illustrate how to merge this binomial heap with another binomial heap, consider for the sake of example binomial heap with 23 elements, with 27 elements. Binary expansion of 27 goes 1, 1, 0, 1, 1. So corresponding to this number or collection of binomial trees in a binomial heap, and corresponding to this binary expansion, which evaluates to 27, as you can calculate. And again, observe the correspondence. 1, 2, there's no binomial tree of order 2 with 4 elements, 8 elements, 16 elements. So that's happening here. Okay, and so this is an example, and now consider how do we add these two binary expansions of integers. How do we add 23 and 27 in binary, not in decimal? In decimal, the answer is 50. But let's do that in binary, taking and recalling all the carries. So we add these two, giving a carry. There's these two and a carry that leaves 2, and another carry 4, and the carried 4 give 8, so no element here. Next digit is 0, and a carry. Adding these 2 gives a carry. Now we're adding these 3. That gives 16 and 1 carry. And finally, here's the carry, and then we're done. Okay. And the same happens in more general form when we merge these two binomial heaps. First, we combine them in these two lists into one list of, this list is in strictly increasing order. This list is strictly increasing order. When we merge them, it becomes non-decreasing order, right? So because now there are and can be various binomial trees of same order, right? So for example, here, these two have the same order, or these two have the same order. So after kind of combining the two lists, we obtain one final list, but a list which may violate the binomial heap property of being strictly ascending. So next we're going to repair that by walking through this new list and combining any two binomial trees that have the same order into one binomial tree of larger order using the merge operation. Remember that merging two binomial trees, we can only merge two binomial trees of same order and right. So we can only merge two binomial trees of the same order, and we can do that in constant time by comparing the roots of these two binomial trees of same order. The smaller one with the smaller root value become the dominant one. The one with the larger value become and one additional child to this previous binomial tree, which remember already had children of all orders up to k minus 2. And now it receives another child of order k minus 1, and thus resulting in a binomial tree of order k. Only binomial trees all have the same, we can only merge two of the same order in constant time. And now let's apply that constant time merge operation to repair that. Here we have two binomial trees of same order, merge them into one binomial tree of higher order, and thus repairing this violation corresponding to the addition of these two digits into with a carry. So that's what we do here, merge. And now we've created another violation, because now we've actually three binomial trees of order 1, but that's the same as we had here in binary addition. We had the carry, and we had these two occurrence of digits with weight 2. So what we do, we add them, two of them. We need to find out which one is the smaller one among the three, and which will become the dominant one, and the largest one will will remain. So we merge them and thus obtain a new binomial tree of order 2, corresponding to the carry here with weight 4. This one will remain, and this one has now created another violation corresponding to another carry here. 4 plus the carried 4 gives rise to the next carry. So we need to merge these two again, and so on, merging these two. So this merge operation can cascade through the entire list, but each time we reduce the number of entries, the number of trees in the list. And so after logarithmically many merge operations, we have reached the end of the list, and we have recovered the condition for binomial heap that each binomial tree order can occur at most once, corresponding to after the binary addition digit-wise with all the carries. We have made sure that in the result, the binary expansion, there's only digits 0 and 1, no more occurrence of a digit 2, which would be indicative of a carry, which we had and have taken care of. So that concludes our discussion or recap of the merge operation of binomial heaps, the arguably most important operation. Yes, I keep emphasizing the similarity of the merge operation of binomial heaps to binary addition of integers, and the number of carries of integer addition is at most log n, where n denotes the value, not the length, binary length of the integers. Similarly, the number of merging trees within, to repair the property of merging heaps, is at most logarithmic. So the overall cost of the merge operation is thus logarithmic, and we already saw and used the merge operation, for example, in the insert operation by creating a one element binomial heap and merging that with the existing binomial heap. We also use the merge operation in the ExtractMin operation, where we removed one tree, then created a lot of orphans, put the orphans into another list, and then merge this new list with the previous existing list to obtain another binomial heap. So we've already tacitly made use of the merge operation, but now we've already also finally discussed and covered the merge operation. So that concludes our recap of binomial heaps and operations on binomial heaps. And just to wrap things up, in this chapter 2, we talked about abstract data types. We talked about ADL trees whose deficiencies that merge is only feasible in linear time. All other operations are logarithmic, but merge is linear time. And now we've concluded also our recap of operations on binomial heaps, where now all operations are possible, feasible in logarithmic time. Insert, delete, and in particular also the ExtractMin operation with the bubbling to repair the heap order, the DecreaseKey operation, and our workhorse, the merge operation in logarithmic time. But let me emphasize that this is still classical algorithm analysis, worst case analysis. And starting with chapter 3, we will look into alternative ways of algorithm analysis. Specifically, chapter 3 is about average case analysis, which arguably could be a more realistic way of analyzing algorithms.